Welcome back from the break. I'm glad that you could join me again. We're going to go on with graphs, but this time we're going to look at the rate of the reaction graphs for Le Chatelier versus time. In our previous session, we looked at the concentration versus time. We will now look at the rate versus time. When a stress is applied to a closed system at a state of chemical equilibrium, what changes will be seen on the graph of the rate of reaction versus time? Now we're going to investigate the same reaction of nitrogen, hydrogen and ammonia, where ammonia is being produced at a temperature of 350 Kelvin. The system is in chemical equilibrium. And now what we need to remember from rate of reaction graphs is, we've dealt with this graph a little earlier, that we said in the beginning it will be fast, nothing, become a bit faster, slower, until a point where the rate of our forward reaction is equal to the rate of the reverse reaction. At this point, we are at chemical, or the system is at chemical equilibrium. Just a little reminder again, when we spoke about rates a few sessions ago, we said that the rate of a reaction can be affected by 6 different factors. We also spoke about the collision theory and how these factors specifically have an influence on the rate. Just as a reminder, we looked at concentration, we looked at surface area, pressure, temperature, addition of a positive catalyst, and also the nature of our substances. Now what we are going to do now is we're going to look at some examples where we will look at the rate graphs for some of these factors. We're still in the closed system and we're still busy making ammonia at 350 Kelvin, and it is at chemical equilibrium. The question here is, a catalyst is added to the reaction mixture. Catalyst, I just want to say that it's a positive catalyst. We know that a catalyst is a substance that does not take part in the reaction, but it lowers the activation energy. Okay, so what will happen to the rate of the reaction? Now when we add a catalyst, we actually speed up the reaction. So which reaction is sped up? The forward or the reverse reaction? Right. When we put or add a catalyst, there is an increase in both the rate of the forward as well as the reverse reaction. But there is no change in the concentration. Remember, I said in an earlier session, the product is formed faster, but the amount of product that forms remains the same. When we look at the rate of the reaction for nitrogen, hydrogen, and the producing of ammonia, we can see that the rate of reaction goes into chemical equilibrium, and when it's now in equilibrium, it's being disturbed by a catalyst. What will happen? Because it's a positive catalyst, it actually speeds up both the reactants, but nothing else will happen. It speeds it up and it goes to a new equilibrium position. When we look at your concentration graph for a catalyst, you can see after disturbance, your concentration graph actually shows that all your concentrations remained the same, constant. Right, now we want to look at the increase in temperature. Now, we are now increasing the temperature to, let's say, 400 Kelvin. An increase in temperature, the rate of the forward and the reverse reaction will both increase initially. the rate of the endothermic reaction will increase more, because it's actually your endothermic reaction that's being favored. But take note, both of the rates will increase at first. When we look at the rate of reaction versus time graph, we can see there's a spike for both the forward reaction as well as the reverse reaction. But the spike for the reverse reaction is bigger because the reverse reaction is the endothermic reaction and the forward reaction is the exothermic reaction. With an increase in temperature, the reverse reaction, being endothermic, was the reaction that was favored. The next one that we're going to look at is an increase in the hydrogen concentration. When we look at an increase in the hydrogen concentration, it is an increase of a reactant. The rate of the forward reaction increases, and it will increase sharply because it will then start to decrease. There was now a lot more hydrogen in the system. What will happen to the rate of the reverse reaction? It will increase slowly. If we look at the rate versus time graph for that increase in hydrogen, we can see because it was an increase in hydrogen and the forward reaction was favored, the spike for our forward reaction is high, no spike for the reverse reaction, but the forward reaction then starts to decrease, and then the reverse reaction starts to increase. When we go look at the features of your rate of reaction graphs, with the addition of a positive catalyst, we had two vertical lines to show that there was an increase. Then we looked at a change in temperature, specifically an increase in temperature, two vertical lines with different lengths. The endothermic was longer because the endothermic was the one favored. Change in concentration, one vertical line, and the other one was a curve. To summarize, remember you must learn your Le Chatelier's principle off by heart. They like to ask that one in the exam. You must recall the factors that will affect the chemical equilibrium. Remember, we have 3 of those. Practice using the answering method that we explained to you today. And only temperature affects the Kc. Recognize how a stress is applied to a system when it's in chemical equilibrium and how that will affect the concentration and the rate versus time graphs. Remember, it's 2 different graphs. This is where we will end our session of today. I would like to thank you for participating. Have a good one.